All right, so the next problem we're going to look at involves a repeating decimal. We've looked at one example like this already with 0.3 repeating. We showed that that can be interpreted as a geometric series that converges. We're going to look at another repeating decimal, which when we evaluate it as a geometric series and find its limit, it turns out to be something that some people find a little counterintuitive. So it's this, the number 0.9 repeating. We're going to show that this decimal, this number, is exactly equal to 1. It's not approximately equal to 1. It's not really, really close to 1. It's exactly equal to 1. And the way that we're going to show that is we're going to represent the number 0.9 repeating as a geometric series. So this number 0.999, but this repeats on forever, can be thought of as 9 times 1/10 plus 9 times 1/100th, which I write as 10 squared, plus 9 times 1/1000th, which we write as 10 to the third power, on and on and on and on. Okay, or in summation notation, I could write that this way. N equals 1 to infinity of 9 times 1 over 10 to the nth power. So this is a geometric series because each term in the series is equal to the previous term times 1/10. So we keep multiplying by 1/10 to get each new term. That means the common ratio for this series, which we call R, is 1/10. The first term in this series, which we tend to call A in that formula for the limit of a convergent geometric series, is this one, 9 times 1/10, or just 9/10. So because my common ratio is between -1 and +1, we know that this series converges, and to find its limit, that's just equal to A, which is 9/10 over 1 minus my common ratio, which is 1/10. However, 1 minus 1/10 is just 9/10. So I have 9/10 over 9/10, and of course anything divided by itself is just 1. So this is a proof, if you will, that the repeating decimal 0.9999 on forever is exactly equal to the number 1. Again, exactly equal, not approximately, exactly. Okay, let's take a look at a tougher example. So this one, we want to determine whether this series, this is the series as n goes from 1 to infinity of 3 to the power of 3n times 5 to the power of 1 minus 2n. We would want to determine if it's convergent or divergent. And the trick to this is going to be putting this in a form that shows that we're looking at a geometric series. Going back to this example, anytime we write a geometric series in summation notation, you can always think of it as some number times some other number to the power of n. The thing that I'm raising to the power of n is going to be that common ratio that we find in those geometric series. So my goal is going to be to try and represent this sum in that form. So to do that, let's take a look at how we might be able to write this a little bit differently. So this 3 to the 3n, I'm going to leave it as a 3 to the 3. Actually, I'm going to do something a little bit different. Let's write it as 3 cubed to the power of n, because that is the same thing as 3 to the 3n. I'm using that power to a power property. And then notice I'm setting up a fraction here. This second factor right here, 5 to the 1 minus 2n, I'm going to write that as 5 to the 2n minus 1 and put that in the denominator. Now notice all that I did is I took the opposite of my power here. And so in other words, 2n minus 1 is negative 1 minus 2n, negative in parentheses 1 minus 2n. Using that negative, I put this thing in the denominator. Okay, now I'm going to manipulate this a little bit. So we're going to have this now. I can write 3 cubed as 27, so this can be written as 27 to the nth power. I don't really need the parentheses there, but there they are. And then 5 to the 2n, I can write as 5 squared to the nth power times 5 to the negative 1 power. Okay, so here I'm using my power to a power property, and then I add a negative 1. That's how we deal with these exponents here. These two things are the same. All right, so that 5 to the negative 1 power, being in the denominator, I can move it up to the numerator and just call it 5. So that's going to be this. 5 times. Now, this is still 27 to the power of n. 5 squared is 25 to the power of n. So I've simplified this a little bit further, and it's starting to look like the form of a geometric series. As a final step, I can write that this way. N equals 1 to infinity. 5 times 27 25ths to the power of n. This is the same as this. I'm just using exponent properties to simplify it. So if you compare this to the form of this other geometric series that we had up here, remember that common ratio is the thing I'm raising to the power of n. So in this case, r, my common ratio, is 27 25ths. Now that is greater than 1. And we know that if the common ratio of a geometric series is greater than 1, then that series diverges. So this is a divergent series. It diverges, okay? So it may not have initially looked like a geometric series, but after some manipulation, some algebraic simplifying and stuff like that, we can see that it did take the form of a geometric series. And that's how we were able to come up with our conclusion. Let's take a look at another one. This time I want to find the sum of the series that goes from n equals 0 to infinity of x to the power of n, where x has an absolute value less than or equal to 1. So now I'm not giving a specific value for x. We're just assuming x is any number whose absolute value is less than 1. Okay, this is also a geometric series because I'm multiplying each new term by another factor of x if I were to write this out. Notice this series could be written as 1 plus x squared plus x cubed plus ... It goes on forever. I start with a 1 because x to the power of 0 would be 1, and we're starting with n equals 0. So this thing is a geometric series. Each new term is just x times the term that came before it. So the x is that common ratio. And then in addition to that, the common ratio, common ratio, has an absolute value less than 1, which means that the series will converge. So that I can say a, my first term is 1. The common ratio r is just x, and so the series is equal to a, or 1 over 1 minus my common ratio, which is x. 1 over 1 minus x. I use this example because we use that exact series a whole lot towards the latter half of chapter 11. So this is a result that we're going to use again later. Okay? All right. So now let's talk about a theorem that's helpful for showing that a series is divergent. This theorem says that if the series, this general series here, n equals 1 to infinity of an is convergent, then the limit of its sequence of terms, so this is the limit of the terms, if you put them into a sequence, is equal to 0. Now this kind of makes sense because in all of the convergent series that we have looked at, in order for it to add up to something finite, the terms have to be getting smaller and smaller and smaller as you go further out in the series. If they don't end up approaching 0, then we're going to keep adding, if all the terms are positive, for example, we're going to keep adding positive large enough numbers to make that series diverge. So this is a necessary condition. If a series is convergent, then a sequence of terms has to go to 0. The converse of this theorem is not true. And if you don't remember what the word converse means, this is an if-then statement. And if I were to switch the statements that show up after the if and the then, I get what's called the converse. So the converse of this theorem would state that if the sequence of terms has a limit of 0, then the series is convergent. And that is actually false. We've already seen an example that proves that false. The harmonic series. If you look at the harmonic series, remember its terms are 1 plus 1/2 plus 1/3 plus 1/4 and so on, right? The sequence of terms here, 1, 1/2, 1/3, 1/4, are clearly approaching 0, but we know that the series diverges. So this only works one direction. Let's prove this, and then we'll talk about how it's useful. So suppose we have the series, and we're going to assume that it's convergent. And here is what its nth partial sum would look like. Sn is equal to a1 plus a2 plus ... plus an. Okay? Now notice also that an is equal to Sn minus Sn minus 1. So what this means is that if I take this nth partial sum, and then I take the nth partial sum that comes right before it, so that would add up all of the numbers except for an. If I subtract those two, an is their difference. Now since this sum is convergent, we know that the sequence of partial sums has to be convergent, because that's how we defined convergent series in the first place, which means that the limit as n goes to infinity of my sequence of partial sums is equal to some finite number s. Okay, now n minus 1 goes to infinity as n goes to infinity. And so if I take the limit as n goes to infinity of a sub n, remember this is going to be the limit of my sequence of terms in my series, that a sub n, like we said up here, is the same thing as Sn minus Sn minus 1. I can distribute the limit to both parts, but both of these limits are going to go to s, so that their difference is s minus s, or 0, and that's the thing that we were trying to prove there. Okay, now like I said when we first got into this series, this theorem, this series is useful for showing, I think I said series again. This theorem is useful for showing that a series is divergent, which seems a little bit odd because it doesn't say anything about divergent here. It says convergent. But again, this is not helpful to show that a series is convergent, because if we're able to show that the limit of the sequence of terms of that series is 0, then the series may converge, it may not. We can't say for sure. However, if this ends up being false, so in other words, if you're looking at a series and you look at the terms of that series, the sequence of terms, and then if you find its limit, if that limit is anything other than 0, then that series could not have converged in the first place. If it did, then that limit would have to have been 0. So what we do with this theorem is we look at a series and we take the limit of its terms, its sequence of terms, and if you get something other than 0, you get to just automatically say this series diverges. Okay? So here, again, I mentioned that the harmonic series is a counterexample to the converse of this thing. It's showing that the converse is not true. And I believe, actually, I'm not sure if we did show that the harmonic series diverges or not, so I'm gonna show that right here. The harmonic series is this series, the sum of these terms 1 over n, so it goes 1 plus 1/2 plus 1/3 plus 1/4. I think, I'm just realizing now, I think I wrote this up here assuming we had already talked about the harmonic series. I don't think we have yet. I'm getting myself a little bit mixed up. So let's take that one from the top. The harmonic series is this series. I mentioned up there that it diverges, but we can show that it diverges down here. So this series, you notice the terms are approaching 0 as n goes towards infinity. And if we look at some of these partial sums, so the second partial sum is 1 plus 1/2. And then we're going to jump to the fourth partial sum, 1 plus 1/2 plus 1/3 plus 1/4. I'm grouping up these terms because I'm going to change one of them and compare this to a different sum over here. If I change that 1/3 to a 1/4, then I'm replacing it with a smaller number, which means this sum is going to be less than this sum. But this sum, if I add up all of the terms, I get 1 plus 1/2 plus 1/4 plus 1/4, which is 1 plus 2 over 2 when I get a common denominator with all of these. Obviously that's equal to 2, but we're going to leave it in that form for a second because we're looking for a pattern. Now I'm going to jump to the 8th partial sum, s sub 8. So that would be 1 plus 1/2 plus 1/3 plus 1/4. This goes all the way out to 1/8. And as before, I'm going to group up these 2 terms, and then I'm going to group up these 4 terms here. So notice if I replace that 1/3 with a 1/4 again, I've replaced it with a smaller number. And then if I replace my 1/5, 1/6, 1/7, all with 1/8, all of those are smaller than the terms I replaced, that I put in there as replacements for. So this sum has to be less than this sum. But when I add up these terms, I get 1 plus 1/2 plus this would be 1/2 plus 4/8, which is also 1/2. So what I'm doing is I'm grouping up terms that add up to 1/2. So I get 1 plus 1/2 plus 1/2 plus 1/2, which is 1 plus 3/2. Then if I jump from the 8th partial sum to the 16th partial sum, I can sort of repeat this process. And if you notice, the partial sums that I'm using are all powers of 2. 2, 4, 8, 16. The next one will be the 32nd partial sum. But when I do this and I group up terms, 2 terms here, 4 terms here, 8 terms here, then those groupings, it's easy enough to see, those would all add up to 1/2 if I replace them all by the smallest fraction in the grouping. So for example, once again, in this grouping, we replace the 1/5, 1/6, 1/7 all with 1/8. Here, I have 1/9 through 1/16. I'm going to replace everything by a 1/16. So everything gets smaller. So this sum is smaller than this sum, but this sum adds up to 1/2. Okay, so you can see you can repeat this indefinitely. You can you can keep finding powers of 2 forever, and every time I find a new one, I can make some replacements to show that the partial sum here is greater than a partial sum that is 1 plus a whole bunch of 1/2. Generally speaking, I can show that the partial sum s2 to the nth power is always greater than 1 plus n over 2 for whatever that value of n was. And if I let n go to infinity, so that I keep taking larger and larger partial sums here, this thing will also go to infinity. But the partial sums are greater than that, so that means that the partial sums are also going to go to infinity. The whole point of all that was to show that even though this harmonic series has terms that are approaching 0, the sum is infinite. It does not have a limit, which means it diverges. Let me turn my camera a little bit. Okay, that's a really, really important counterexample. So, using that theorem, we have this thing that we call the test for divergence, or sometimes just the divergence test. What it says is that if the limit of your sequence of terms, so the limit as n goes to infinity of a sub n, either does not exist or is not equal to 0, then that series that adds up those terms is divergent. So we're going to use that here. Show that this series diverges. So what I'm going to do is, instead of dealing with the series directly, I'm just going to look at its sequence of terms. We're looking specifically at this sequence right here, 2n minus 1 to the second power over 3n squared. Okay? If I take the limit as n goes to infinity, I want to show that I get something that's not 0. So there's a couple of ways of handling this. One way is to actually expand out that numerator. So I would get 4n squared minus 4n plus 1 over 3n squared. Notice I have an n squared term showing up in each one. I'm going to do a little algebraic trick where I multiply the numerator and denominator of this thing by 1 over n squared. So that's going to give me a 4 there, minus a 4 over n there, plus a 1 over n squared there. And then down here, I'm going to get 3. Okay? Now, as n goes to infinity, these two denominators are going to get really, really big, which means these two expressions in my numerator are both going to go to 0. So that's going to leave me with 4 over 3, or 4/3 as n goes to infinity. So this is not equal to 0. Since 4/3 is not equal to 0, the series diverges. Okay, that's how you want to use that test. All right, a couple of theorems, or a couple of properties of convergent series. So if you have the sum of these ANs and the sum, or the series of these BNs and ANs, if they are both convergent, and if c is some constant, then the sum of the series that adds an and bn and the series that subtracts an minus bn are both going to be convergent, and we also have these properties. So the sum of the series of the form c times an is equal to c times the series of just an. So in other words, you can pull this c out of an infinite series like that. You can also break series up into sums or differences like these are showing. So down here we have a proof of the second part of this. I'm not going to read through this proof, but it's there if you want to look at it later, just kind of for reference. It's just showing you that if these two series are convergent, then the series that adds up the sum of an and bn is just equal to the sum of the series of an's plus the sum of the series of bn's. Again, you can go through that proof on your own if you want to see it. And that's kind of where this leaves off. Here's the last little line of that proof. So this is going to wrap up section 11.2.